We're going to start this lecture by looking at aromaticity, and in particular where it's kind of coming from or why we discuss this. So if we were to consider, say, benzene, which I know isn't drawn there, but if we drew that in really quickly, benzene is a six-membered cyclic ring with double bonds alternating all the way around it. Okay? And so we might wonder, well, why so much interest in benzene? Okay, well, the first thing we should do is consider what it has in similarity to other cyclic six-membered rings. So if we looked at cyclohexene, which is one double bond, we could look at its reactivity, or really how it would react when accepting hydrogen and going to the fully saturated cyclohexane. So we could add hydrogen and we could look at the heat of hydrogenation. Okay, so the heat of hydrogenation is merely the energy released when we add hydrogen. Okay, and yes, we should release energy. This should be an exothermic reaction because, well, something special about this structure that would cause it to be higher in energy than our cycloalkane. Okay, which is a good question. What happens if we add a second double bond? Let's say we drew out our structure and now we have two double bonds. Well, what would we expect to happen to our heat of hydrogenation? Okay, well, it should go up, okay, but we also have two possibilities. Okay, we could have had the double bonds away from each other or close to each other. And remember kind of our structure on benzene. Well, if one double bond produces 120 kilojoules per mole of energy, what would we expect in a situation where we have two double bonds? Well, we might expect double that, and we might expect something like 240 kilojoules per mole. Okay, but before we get too excited about that number, is there a difference between these two structures? Hopefully what you recognize is the red one is lower in energy. Okay, well, if it's lower in energy, it shouldn't be 240. Okay, it should be something a little bit lower than that. Okay, and why is it lower in energy? That's also a good question. If we actually look at the structure when we now do our heat of hydrogenation, sure enough, we're getting 232 kilojoules of energy released. Okay, so that's pretty darn close to our 240. So we get a little bit of stabilization due to the resonance. Not a whole lot, okay, but it's there. So what might we predict to then happen, say, for benzene, which was our six-membered ring with now three double bonds? Well, our first pass is three double bonds, so 360 kilojoules per mole. But that's a bit of an overstatement, as we just discussed, because, well, there's resonance in benzene. Well, resonance accounted for maybe 8 kilojoules per mole. So let's go ahead and subtract 16, and because I don't want to do the math, let's just make it a nice even 20. So we might predict 340 kilojoules per mole for benzene. Okay, so those aren't bad predictions. We're just working through the information that we're given. Okay, and here the textbook slide is a bit off because, yeah, they're going, oh, it should be 360, but we do have that resonance effect. Okay, but what do we actually see? Well, we actually observe 208 kilojoules per mole. We add a double bond, thereby increasing the energy, and yet somehow by adding that double bond, I'm less energetic than if I had just two double bonds. How does that work? What is going on there? There's 152 kilojoule per mole difference here. That's pretty astonishing. Okay, well, how and why? What is happening there? Okay, and since I won't ask this then obvious question, well, the reason, of course, as is all things with organic chemistry, is resonance. Okay, but let's address that resonance a little bit closer, because the first one gave us resonance already, okay, when we had our double bond. So when we go through and draw out our resonance structure for our diene, help, get it? We got a negative and a positive in our resonance structure, which makes sense. We started neutral, we should end neutral, I'm going to end up with those two charges. What happens if I go through and do that same idea for the benzene? Okay, well, I've got more resonance to worry about, so I've got to draw all that out. And in the process of drawing that out, what do I find? Okay, well the first double bond moved to here, second double bond moved to here, and the third one moved here. So the result is I just kind of alternated the double bonds around. Okay? But there's an interesting feature about this resonance structure that is drastically different from our diene. There's no charge. What does that mean for its stability? Well, it is actually more stable than our diene because we don't generate charge when we generate that resonance structure. That's pretty phenomenally fascinating. And that's one of the reasons, or the primary reason, why we have such a lower energy structure. So when we're looking at our aromatic structures or our benzenes, they're very, very low in energy because of this resonance contribution. That resonance contribution is such a large effect to its stability that we often don't show the double bonds in benzene, and we instead show it with a circle, representing that the electrons of your 3 double bonds are now being shared equally all the way around that ring. This is also why when we looked at HNMR and all of that, we only see one hydrogen, or we see lots of symmetry within the molecules when we look at our HNMR. Okay, so kind of a neat little observation for our benzene. And so our driver behind this is that it's a fully conjugated cyclic compound. So of course the next question we would then ask is this going to affect our reactivity? Well, if it is an exceptionally stable molecule, should it be reactive? Well, logically, no. So what happens? Well, sure enough, if we look at our benzene structure, we don't get Diels-Alder reactions, and we don't get our standard additions. Remember the Diels-Alder? We needed a diene and a dienophile. Benzene could supply a diene and at the same time supply a dienophile. No Diels-Alder reactions. Interesting. We also don't get addition. Okay, also interesting. What makes this even more kind of fascinating is that someone went through to try and monitor or replicate benzene's incredible stability and found that there were other molecules that did the same thing. Okay? So if we take a look at, say, cyclopropyl, okay, this one's a little bit tricky because we have a positive charge in there and the double bond. But interestingly enough, this structure won't work in a Diels-Alder reaction, even though it's an alkene. We might even predict it to react faster because it's cyclopropyl. It might want to break open. And we also don't get any addition. Well, that's kind of neat. Right? Well, are there other structures that we could look at? And the text is going to give this away, but oh well. If we increase the size of our ring, okay, from the cyclopropyl, we go up to cyclobutane, okay, or butene, butadiene. Okay, so just an extra carbon with now the double bonds, just like we saw in the benzene, or a cyclooctatetraene. Okay, same idea, double bonds all the way around. We can do resonance all the way around for these. Okay, we have that even resonance, which technically would actually show that as a resonance structure. Okay. And so we might say, well, okay, they match the similarities of our benzene and our cyclopropene, or propenyl cation. So we would not expect them to undergo Diels-Alder reactions or standard addition. Unfortunately, that's not true. Okay? Interestingly enough, those structures do run reactions under Diels-Alder conditions, and they do additions. So something weird is going on here. Right, well, this takes a little bit of time to process, and someone went through and compared a whole bunch of different cyclic structures that had conjugated double bonds and came up with a rule set to apply those. That rule set is typically referred to as Huckel's rule, because Huckel was the guy that figured this out. And so if we're going to define a compound as being aromatic, we've used aromatic to refer to benzene consistently throughout the semester, and a bit non-correctly because we haven't defined what aromatic was. Okay, well, here's our definition. We must have a fully conjugated ring with overlapping p orbitals. Well, every example on this screen, okay, except for those products, so we can temporarily erase those, satisfies those rules. Okay. The next part is it must meet what's known as Huckel's rule. We have to have an odd number of electron pairs. So if we go through and look at benzene, how many electron pairs are there in the ring structure, okay, or accessible for resonance? Well, I have 1 pi bond, 2 pi bonds, 3 pi bonds. I have 3 pairs. In the cyclopropenyl cation, I have 1 pair. Well, both 1 and 3 are odd numbers. Okay, that's why we laugh at them when we see those numbers. When we move to the cyclobutadiene, there are 2. Well, that's an even number, not an odd number. And the octotetraene, sure enough, we have 4 pairs of electrons. Okay? There are a few where we could bring in this formula comparison if you wanted. It's up to you. Okay? So the odd number of electron pairs can be referred to as our 4n plus 2 total pi electrons, where n is any arbitrary number. Okay, so what do we mean by that? So what we're saying is that if we look at the pi electrons in benzene, there are 6 pi electrons. Okay? If I set up my equation, 4n plus 2 must equal 6. Okay, well, to do that, hopefully you can recognize that n must equal 1. Well, n is a valid solution to this. Okay? That n holds no other meaning than as a possible variable that allows me to solve this question. Okay? When you might say, well, but the cyclobutadiene is going to do the same thing, won't it? Okay, well, there's 4 pi electrons. If we set up our same equation, 4n plus 2, what must n be to solve this equation? Well, n has to be a half. Notice a half is not part of the rule set for Huckel's rule. N must be a whole number, 0, 1, 2, or a whole integer value. Okay? So cyclobutadiene does not satisfy Huckel's rule. Okay, so this is looking at our aromatic compounds. So those are our primary criteria. Okay, so why is cyclobutadiene not particularly stable and yet benzene is? Okay, well, we can use molecular orbital theory, everybody's favorite, to try and predict something about this stability. Okay, and that would involve drawing out a whole bunch of molecular orbitals. Notice that I've provided 2 of them. Okay, I've provided the lowest energy molecular orbital for both cyclobutadiene and cyclohexatriene. And for those of you freaking out at cyclohexatriene, that is also known as benzene. It's the same thing. Okay? And if we were to go through and look at how we would draw or fulfill our electrons, well, in cyclobutadiene there's 4 pi electrons. So I want to put them into my orbital. Well, I'll put them the lowest energy first, then I'll move to the highest energy. Ooh, interesting. My highest energy electrons are unpaired, which means there is an empty space that I could place an electron. They are asking for electrons. That could explain its reactivity. Well, what happens in the case of benzene? Well, in the case of benzene, we had 3 pi bonds, which equals 6 pi electrons. We need to place those 6 electrons in. There's 1, 2 at our lowest energy, 1, 2. Oh, we're going to have the same issue as we had for our cyclobutadiene, except I put in my next 2 electrons. The interesting feature here is that now all of my orbitals that have electrons are full. There is no empty space to place electrons, okay, at least at low energy. I would have to go at a higher energy state, and then in which case they would be unpaired, which is making them even a higher energy state. So what does that mean? Well, that means that benzene is incredibly stable, and the cyclobutadiene is not. Okay? To draw out these molecular orbitals, we have to go through and say, okay, well, we've got all of our p orbitals. We could shade up, we could shade down, we could shade up, we could shade down, and we'd have a lot of trouble to go through and do this. Okay? And that's a bit of a tedious process. It might be nice if we could come up with some kind of shortcut. Thank you, presumably Mr., but it could be Miss or Mrs. Frost, because I don't know. We can predict the energy and shapes of our molecular orbitals through complex calculations. but we could use a frost circle to predict their relative molecular orbital energies, which is what we did over here. We aren't quantifying anything, we're just saying this is where they are relative to each other. So when we go to a frost circle, it's going to set us up pretty darn close. So our steps: draw a circle. Well, that was challenging. Well, actually, that could be pretty challenging. We then want to inscribe the shape of our organic molecule within that circle. We want to make sure that your lowest energy, so one of your points, is at the very bottom. Okay, well, and that makes sense because we'll only have one lowest energy molecular orbital where they're all overlapping. Okay, so that explains why the point needs to go down. At each of the points where they touch the circle, we just draw a line representing our orbital. Roughly through the center of the circle, we can draw a dotted line to give us our non-bonding energy. And then anything above that line is anti-bonding, too high in energy. Everything below that is bonding. Okay, that's not too bad. So let's take a look at an example. So if we take a look at the cyclobutadiene, because of course that's the easy one, I'm going to make you do the other one. There's my circle. I said it could be difficult. We want to take the shape of our cyclobutadiene, which was a square, and I want one of those points to be at the bottom. Well, if I now inscribe a square into this, don't make fun of my square. I now have my square. Through the center of my circle, I can draw my dotted line. I then have a bonding orbital at the bottom. I have two non-bonding orbitals and one anti-bonding orbital. That's it. That's my frost circle. I could then go through and add the electrons from my structure. I know I have 4 pi electrons because I had 2 pi bonds. 1, 2, 3, 4. I have unpaired electrons, super reactive molecule. Go ahead and do the same thing for benzene. Okay, and theoretically you already know the answer, but you could go ahead and try and set that up and make sure you get the same result. Okay, so here's our big summary of rules. Okay, we have aromatic compounds, which we discussed. Okay, you should already be good with those. Unfortunately, we have this other category, or at least 2 other categories. Number 1, what if, say, rule 1 is completely invalid? We don't have p orbitals. Well, we shouldn't call it aromatic. We should call it something other than aromatic. Okay, so we could call it anti-aromatic. But the problem with that is we also had cases where we had structures that had fully conjugated ring with overlapping p orbitals, like our cyclobutadiene. Okay, so there's actually 2 conditions or 2 sets of possible structures that would not match our aromatic definition set. So we end up with 2 new classifications. We have the anti-aromatic compounds and we have the non-aromatic compounds. The non-aromatic should be straightforward. They just don't match. We wouldn't even consider them. Most alkenes, or all alkenes really, would be non-aromatic. Okay? So in an anti-aromatic compound, you'll notice the rule sets are very similar to aromatic. Okay? We still have to have a fully conjugated ring with overlapping p orbitals. Okay? The trick here, though, is we will have an even number of electron pairs, or 4n total pi electrons. Okay? Where n, again, is 0, 1, 2, 3, 4. Okay? However you want to remember that is entirely up to you. We'll discuss in class some other possible memorization techniques. The non-aromatic, okay, will invalidate one or all of the rules in our aromatic and anti-aromatic compounds. I will admit there is a trick question that's involved in our non-aromatic. The anti-aromatic compounds are very reactive. Okay, so what our anti-aromatic compounds will try and do is minimize that reactivity by adjusting their structure. Okay, they will adjust their structure by preventing the overlapping of pi bonds, okay, or the overlapping of p orbitals. So if it can prevent that from happening, well then it's not really invalidating the rules as we look at the structure. The structure is changing its molecular shape in a way that's hard for us to visualize, that makes it no longer anti-aromatic. Yeah, I know, it's not a happy thing, okay? But that's what's happening. The structure will tweak its shape and prevent the overlapping of p orbitals, so then it's not technically anti-aromatic anymore, it's non-aromatic. That's the trick question. Most of our non-aromatics are straightforward. Okay, so we have to watch out for the anti-aromatics. They can be a big old thorn in our side. Okay, so all of our examples have been through a carbon pi system. So this is an interesting question, one that is not presented in your possible answer choices down here, or your possible questions down here. Do we have to use carbon in our pi system? Could we use different atoms to supply those electrons? It's a challenging question, one you should think about or read about before Wednesday. Okay. Aromatic compounds fulfill these criteria. Take a look at these three compounds and define them as either aromatic, anti-aromatic if you can, or non-aromatic. Okay, so I'll give you a second to answer the first one. Hopefully a little bit longer than a second because it takes time for the homework or the question assignment to go through and track for the second one. And now for the third one, hopefully again I'll be able to trigger it. And then really we just have kind of a run out in the video because it needs to be far enough away from the previous question to end the question or end the lecture. So we'll pick up there on Wednesday. Thanks for watching the video. If I can find the stop button.